A microwave receiver does not see the sky the way your eyes do. It does not find the stars first, or the bright planets, or the pale band of the Milky Way crossing from horizon to horizon. It measures power, frequency, temperature, and noise. It listens to wavelengths too long for vision and too cold for ordinary intuition. On a clean map, after the foreground glow of our own galaxy has been modeled and subtracted, the whole sky becomes a modeled oval of red and blue. Not a photograph of galaxies, not a picture of nebulae. A record of tiny temperature differences, only a few hundred millionths of a degree from place to place, spread across everything we can observe. This is the cosmic microwave background, the oldest light we can still detect directly, released when the universe was about 380,000 years old and still carrying a pattern from a time before stars existed. The strange thing about this light is that it comes from every direction at once: a telescope pointed above the desert, a radio dish in New Jersey, a satellite far from Earth, and a detector at the South Pole are all looking into different parts of the same ancient surface. The signal is not coming from an object in one region of space. It is not a single explosion frozen somewhere in the distance. It is the cooled remnant of a hot early universe, stretched by cosmic expansion until what began as visible or infrared light became microwave radiation. Today, its average temperature is about 2.7 Kelvin, only a few degrees above absolute zero, and yet that faint background is one of the strongest pieces of evidence that the universe had a dense, hot beginning. If ancient light like this is what brings you back to the deep past of the cosmos, subscribing keeps the next long journey close. To understand why the cosmic microwave background matters, it helps to begin not with a galaxy, but with a limit. Telescopes can look very far, and because light takes time to travel, far away also means long ago. A galaxy whose light has taken 10 billion years to reach us is seen as it was 10 billion years in the past. With infrared observatories, astronomers now find galaxies so distant that their light began its journey when the universe was only a few hundred million years old. But the cosmic microwave background comes from earlier than those first visible galaxies. It is not starlight. It is not the glow of dust heated by newborn suns. It is the last scattering of ancient photons, the moment when ordinary light finally stopped being trapped by the particles around it and was able to move freely through space. Before that moment, the universe was not empty darkness. It was filled with a hot plasma, a dense mixture of electrons, protons, helium nuclei, neutrinos, photons, dark matter, and whatever else current physics requires but cannot yet fully describe. Photons were present in enormous numbers, but they could not travel far. Free electrons scattered them again and again, in the same basic way that fog scatters the light from a headlamp. If you had tried to see across the early universe, there would have been no clear line of sight. The light was everywhere, but it was not transparent. Every photon was jostled, redirected, absorbed, and re-emitted so often that the universe behaved less like a window and more like a glowing wall. That wall was not a solid surface in space. It was a time in cosmic history. As the universe expanded, its temperature fell. Expansion did not mean that matter was flying into a pre-existing empty room. It meant that space itself was stretching, and with that stretching came cooling. The wavelengths of light lengthened, the energy of each photon decreased. Particles that had once been too energetic to remain bound began to settle into more stable arrangements. After about 380,000 years, the universe cooled to around 3,000 Kelvin, cool enough for electrons and protons to combine into neutral hydrogen atoms, without being immediately torn apart by the surrounding radiation. This transition is often called recombination, though in the ordinary sense the electrons and protons were not coming back together after a previous long partnership. They were joining into neutral atoms in a lasting way for the first time. It did not happen everywhere in one instant. The universe had density variations, temperature differences, and local conditions that changed how quickly matter and radiation decoupled. But across a relatively narrow slice of cosmic time, the fog lifted. Free electrons became scarce. Photons that had previously scattered after short distances now found the space between particles open enough to cross billions of light years. The light that escaped then is still arriving now, stretched into microwaves and cooled almost to the temperature of the deep cosmos itself. The numbers are difficult because they are both small and immense. The cosmic microwave background fills space with roughly hundreds of photons in every cubic centimeter. That sounds crowded until you remember that each photon carries very little energy today. Across the full sky, the radiation is almost perfectly uniform. Its average temperature differs only slightly from one direction to another. But those slight differences are the entire reason the map is so important. The fluctuations are about 1 part in 100,000, and they correspond to tiny variations in density and temperature in the early universe. Variations that later became the starting conditions for galaxies, clusters, filaments, and voids. A red patch on a processed CMB map is not hot in the way a flame is hot. A blue patch is not cold like ice. The colors are chosen to make differences visible to human eyes, and those differences are extremely small. Without processing, the map would be almost featureless, a uniform microwave glow across the sky. With careful calibration, subtraction, and comparison between frequencies, a pattern emerges. It looks like static, but it is not random instrument noise. It is a fossil of conditions in the early universe, a pattern that carries information about matter, radiation, geometry, expansion, and the balance between ordinary atoms and invisible dark matter. The cosmic microwave background was predicted before it was detected. In the late 1940s, work connected to the hot Big Bang picture suggested that if the early universe had once been extremely hot and dense, its leftover radiation should still exist, cooled by expansion into the microwave range. This was not a decorative idea. It was tied to the physics of light elements, especially hydrogen, helium, and lithium, which could form only under particular early conditions. The prediction was rough by modern standards, and the temperature estimates were not exact, but the important point was clear. A hot early universe should not leave only galaxies behind. It should leave radiation behind, spread through space, weakened but not erased. Then, in the 1960s, a horn antenna at Bell Labs in Holmdel, New Jersey, began picking up a stubborn excess signal. Arno Penzias and Robert Wilson were not trying to prove the Big Bang when they first confronted it. They were working with a sensitive microwave antenna and trying to understand noise that would not go away. They checked equipment. They considered radio interference. They cleaned out pigeon droppings from the antenna, because even something that ordinary can matter when the signal is faint enough. The excess remained, coming from all directions and corresponding to a temperature of only a few Kelvin. It was not local. It was not the instrument. It was the background radiation the hot Big Bang model had implied. Discoveries sometimes arrive as images, but this one arrived first as a problem in a receiver. A signal that should not have been there became one of the foundations of modern cosmology. Nearby, a Princeton group had been preparing to search for the same radiation deliberately, and the connection was quickly recognized. Penzias and Wilson had detected the cosmic microwave background by accident, but the accident was not meaningless. It was the kind of accident that becomes possible only when instruments become sensitive enough to reveal what older tools could not separate from the noise. In 1978, they received the Nobel Prize in Physics for a discovery that changed the status of the Big Bang from a broad theoretical framework into a model with direct observational support. Yet the early detection did not show the detailed pattern we know today. It showed that the background existed and that it was remarkably uniform. That was powerful. But it also raised a question. If the young universe had been almost perfectly smooth, how did galaxies form at all? Gravity needs irregularities to amplify. A completely uniform sea of matter would remain uniform. Cosmologists expected tiny differences, small enough to be difficult to find, but large enough to grow over billions of years into the cosmic web. The challenge was measuring them. The signal was faint. The Milky Way was bright in many microwave frequencies. The atmosphere, the telescope, the detector, and Earth itself all had to be treated as possible contaminants. NASA's Cosmic Background Explorer, or COBE, was launched in 1989 to make that problem a space mission. Above the thickest parts of the atmosphere, COBE carried instruments designed to measure the diffuse infrared and microwave radiation of the universe. One of its key instruments, FIRAS, measured the spectrum of the cosmic microwave background with extraordinary precision and showed that it matches a nearly perfect blackbody curve. That result mattered because a blackbody spectrum is exactly what a universe once in thermal equilibrium should produce. The radiation had not been assembled later from scattered sources. It carried the thermal signature of a dense early cosmos. Another COBE instrument, the differential microwave radiometer, searched for tiny anisotropies, the slight temperature variations across the sky. When those variations were announced in 1992, they were at the level of roughly 1 part in 100,000. That is small enough to sound almost irrelevant, but it is not. If the average temperature is about 2.7 Kelvin, the variations are measured in microkelvin, far below anything human senses could distinguish. Yet in those faint differences were the seeds of structure. Regions that were slightly denser had a little more gravity. Over time, after the universe became transparent and matter could collapse more freely, those regions began gathering material into clouds, stars, galaxies, and clusters. The first COBE maps look crude compared with modern images, with broad patches and limited angular resolution. But they were a beginning. They showed that the background was not perfectly smooth. They gave cosmology a sky map of the early universe, rather than only a temperature and a theory. Later missions would sharpen the view, but the basic transformation had already happened. COBE measured the CMB as a physical relic with a spectrum, an average temperature, and a pattern of small variations. It turned the background from a discovered glow into a field that could be mapped, modeled, and compared against detailed predictions. WUMAP, the Wilkinson Microwave Anisotropy Probe, followed with better resolution, better sensitivity, and a more detailed strategy for separating the CMB from foreground emission. Launched in 2001, WUMAP observed from near the second Lagrange point, a region of space where a spacecraft can maintain a stable observing geometry relative to Earth and the Sun. Its maps showed the same sky with more detail, turning broad COBE features into a clearer pattern of warm and cool spots. WUMAP helped constrain the age of the universe, the density of ordinary matter, the density of dark matter, and the contribution of dark energy in the standard cosmological model. Then came Planck, launched by the European Space Agency in 2009. Planck observed the whole sky across a wide range of microwave and far infrared frequencies, using instruments cold enough to detect extremely slight variations in radiation. It was not only looking at the CMB, it also had to see the foregrounds that obscure it, dust in the Milky Way, synchrotron emission from charged particles spiraling through magnetic fields, free emission from ionized gas, compact sources, and other signals that sit between us and the ancient background. The final CMB map is therefore not simply what the spacecraft saw. It is what remained after teams modeled, compared, removed, and tested the sky at many frequencies. The Planck map is one of the most important images ever made of the universe, though it does not look like a normal photograph. It is an oval projection of the entire sky, showing radiation that was released long before the first star ignited. The modeled pattern represents density differences in the young cosmos. Each spot is not a galaxy. Each spot is a region of early matter and radiation projected onto the surface from which the photons last scattered. The image is based on data from the Planck mission's final release, and it sharpened many of the parameters in the model now used to describe cosmic history. To call the CMB the oldest light in the universe is mostly right, but the phrase needs care. It is the oldest light we can observe directly as electromagnetic radiation across the sky. It is not the first light that ever existed, because photons existed earlier, trapped in the plasma. It is not a view of the exact first moment. It does not show the Big Bang itself. It shows the universe after it had cooled enough to become transparent, and therefore it marks a horizon for ordinary light. Earlier times are not dark because nothing happened there. They are hidden because light from those times could not travel freely to become an image. This is why the CM sits at the edge of observable electromagnetic history. Beyond it, looking backward, the universe becomes opaque. A more powerful optical telescope will not see through the surface of last scattering, because the obstruction is not technological in the ordinary sense. It is physical. Before recombination, photons were coupled to charged particles. They did not carry straight-line images across the cosmos. To study earlier eras, scientists must use indirect evidence, mathematical models, particle physics, primordial element abundances, gravitational waves if they can be detected, and subtle imprints left on the CMB itself. One of the deepest questions is how those tiny irregularities began. The standard picture suggests that the seeds of structure were laid down extremely early, perhaps during an inflationary phase when the universe expanded by an enormous factor in a tiny fraction of a second. Quantum fluctuations, stretched to cosmic sizes, could become the starting pattern for later density variations. That idea is powerful, but it is not a completed photograph of the beginning. Inflation explains several features of the observed universe, including its large-scale uniformity and near-flat geometry, but the details of what drove inflation remain uncertain. The CMB is one of the main places where scientists look for evidence that can support, constrain, or challenge those early universe models. The map is not interpreted only by looking at spots. Cosmologists use something called the angular power spectrum, a way of describing how much temperature variation exists on different angular scales across the sky. Instead of asking only where the hot and cold spots are, the power spectrum asks how large they tend to be and how strong the pattern is at each scale. Peaks in that spectrum correspond to acoustic oscillations in the early plasma, waves of compression and rarefaction moving through a mixture of photons and ordinary matter under the influence of gravity and radiation pressure. In the early universe, slightly denser regions pulled matter inward by gravity, but photons exerted pressure, resisting collapse. This created oscillations, something like sound waves, though the medium was not air. It was a hot plasma of matter and radiation filling the universe. The largest regions had time to compress once before photons decoupled. Smaller regions had time to compress and rebound. Still smaller ones completed more cycles. When the universe became transparent, those oscillations were caught in the CMB pattern, leaving a series of peaks that act like a record of conditions in the young cosmos. The first peak in the CMB power spectrum is especially important because it tells us about the geometry of the universe on large scales. If space were strongly curved, the apparent size of the temperature spots would be shifted, much as objects appear distorted through a curved lens. Observations from WMAP and Planck indicate that the universe is very close to spatially flat on large scales, within measurement limits. This does not mean the universe is simple or fully understood. It means that one major property of its large-scale geometry is constrained by the way ancient sound waves appear projected across the sky. The relative heights of the peaks tell another part of the story. Ordinary matter, made of atoms, interacts with photons before recombination. Dark matter does not interact with light in the same way, but it still contributes gravity. The balance between baryons, dark matter, photons, and expansion changes the pattern of acoustic peaks. By fitting models to the observed spectrum, cosmologists estimate how much ordinary matter and dark matter the universe contains. The result is one of the most striking conclusions in modern astronomy. The stars, gas, planets, dust, and living bodies made of ordinary atoms are only a small fraction of the total cosmic inventory. Dark matter in this context is not a mysterious glow hiding behind the map, it is inferred from gravity. The CMB does not show dark matter as a color or an object. It shows the gravitational effect that unseen mass had on the early plasma and later on the path of CMB photons as they crossed the growing cosmic web. Galaxy rotation curves, gravitational lensing, cluster dynamics, and large-scale structure also point to the same broad requirement. The CMB strengthens that picture because it finds dark matter written into the universe before galaxies, before clusters, and before the familiar architecture of the night sky had formed. Dark energy enters the story differently. It is not needed to explain the existence of the CMB itself, but the same cosmological model that fits the CMB also connects to the later expansion history of the universe. Supernova measurements, baryon acoustic oscillations, galaxy surveys, and CMB data together indicate that cosmic expansion has been accelerating in recent billions of years. Dark energy is the name given to whatever is causing that acceleration, or to the effective behavior in the equations. It is not a simple substance that has been directly captured. The CMB helps establish the initial conditions from which the later expansion history can be inferred and tested. In this way, a microwave map from the early universe becomes a reference point for almost everything that followed. It tells us how smooth the universe was. It tells us how uneven it had to be. It tells us what scale the first fluctuations occupied. It gives a snapshot before stars, before heavy elements, before planets, before the chemistry of life. The Milky Way, with its spiral arms and central black hole, was not present when this light began traveling. The Sun did not exist. Earth did not exist. Even the atoms heavier than lithium were almost entirely absent because the first stars had not yet forged them. The early universe did contain hydrogen and helium, with traces of deuterium, helium-3, and lithium produced in Big Bang nucleosynthesis during the first minutes. That earlier process is studied through element abundances, not direct light from the first minutes. By the time of the CMB, nuclei and electrons were becoming neutral atoms, but the universe still had no stars to illuminate it from within. After recombination came a period often called the Cosmic Dark Ages. The phrase can be misleading if it suggests emptiness. Matter was present, gravity was working, and density differences were slowly growing. But there were not yet luminous stars and galaxies filling space with local sources of light. During the Dark Ages, hydrogen gas followed the gravitational pull of dark matter concentrations. Slightly denser regions became more dense. Gas fell into dark matter halos. Cooling processes allowed some of it to collapse further. Eventually, the first stars formed, likely massive, short-lived, and chemically simple compared with later generations. Their radiation began changing the gas around them. The first galaxies followed, faint by modern standards but important enough to begin ending the Dark Ages and transforming the intergalactic medium. The CMB had already been traveling for tens or hundreds of millions of years by then, crossing a universe that was slowly becoming structured. The oldest light, therefore, does not show the first stars, but it made the first stars possible by carrying the imprint of the conditions from which they grew. The map is not a photograph of the cosmic web, but it contains the earliest measurable pattern that later became the cosmic web. The large filaments of galaxies and dark matter that stretch across billions of light years did not appear suddenly. They developed from small density contrasts under gravity, shaped by expansion, dark matter, ordinary gas, radiation, and time. Imagine a simulation frame, not as fantasy, but as a calculation. At first, it begins with tiny differences in density taken from a pattern like the CMB. Matter is distributed almost evenly. Then the clock advances. Dark matter clumps first, because it is not pushed around by photon pressure in the same way ordinary matter had been before recombination. Gas follows into the deepening gravitational wells. Filaments sharpen. Voids become emptier by comparison. Where filaments intersect, clusters form. Within smaller halos, galaxies assemble through collapse, mergers, gas cooling, star formation, feedback, and the slow reshaping of structure over billions of years. Simulations are not proof by themselves, they are tools. A simulation can look convincing and still be wrong if its assumptions are wrong. The strength of the CMB is that it provides measured initial conditions that can be tested against the universe we observe later. Galaxy surveys, cluster counts, weak lensing maps, and measurements of baryon acoustic oscillations all become part of the comparison. When the same broad model can connect the early microwave sky to the large-scale distribution of galaxies, it becomes harder to dismiss the CMB as only a strange background signal. It becomes a starting map for cosmic history. The CMB also carries polarization, a subtle orientation pattern in the microwave light. Polarization arises when photons scatter in an environment where radiation has a directional imbalance. In the early universe, Thomson scattering off free electrons produced polarized light under the right conditions. Measuring that polarization is harder than measuring temperature because the signals are weaker and more easily contaminated by foregrounds. But polarization adds another layer of information, separating patterns into E modes and B modes and offering ways to study reionization, gravitational lensing, and perhaps traces of physics from extremely early times. E-mode polarization has been measured clearly and helps confirm the same basic cosmological picture seen in temperature anisotropies. B-modes are more complicated. Some B-mode polarization is produced by gravitational lensing, as the large-scale distribution of matter subtly distorts E-mode patterns while CMB photons travel across the universe. A more primordial B-mode signal, if detected with convincing separation from foregrounds, could point toward gravitational waves from inflation. That possibility is one reason CMB polarization remains such an active field, but it is also a field where caution is essential. Dust in our own galaxy can mimic patterns that look cosmological if it is not modeled correctly. The history of CMB polarization includes warnings about how difficult this work is. A signal can appear exciting, pass early checks, and still become less certain when better foreground measurements arrive. This is not failure in the simple sense, it is how difficult science corrects itself when the target is faint and the foreground is complicated. Galactic dust grains aligned with magnetic fields emit polarized radiation. Synchrotron emission can also be polarized. Ground-based telescopes must contend with the atmosphere, scanning strategy, calibration, detector systematics, and limited sky coverage. Space missions avoid some problems while facing others. A clean CMB map is therefore not a casual picture. It is the end of a long argument with the data. Each frequency channel is compared with the others. Known foregrounds are modeled. Masks are applied to regions where contamination is strongest. Instrument noise is estimated. Independent pipelines are tested. Simulated skies are created to see how often a pattern might appear by chance. The final image looks simple because the work behind it is not visible. The ancient light has to be separated from everything younger that lies between us and it. Our own galaxy is one of the largest obstacles. The Milky Way contains dust, gas, magnetic fields, cosmic rays, compact sources, and diffuse emission that glow in microwave and infrared wavelengths. In an all-sky map, the galactic plane cuts across the view as a bright band. That band is not a defect, it is the material of our own galaxy seen edge-on from inside. To study the CMB, scientists must distinguish the nearly uniform ancient background from the foreground structures of the Milky Way, and that requires observing at multiple frequencies because different physical sources have different spectral behavior. The fact that foregrounds are troublesome does not make them useless. Planck and other missions produced valuable maps of galactic dust, magnetic fields, compact sources, and other astrophysical components while trying to isolate the CMB. The sky is layered. One experiment aimed at the early universe also becomes a survey of the intervening universe. In the same data, there is the glow of dust from our galaxy, radiation from distant galaxies, clusters that leave subtle imprints, and behind all of it, the older microwave pattern from the surface of last scattering. Galaxy clusters leave one of the more interesting secondary marks on the CMB through the Sunyaev-Zeldovich effect. When CMB photons pass through hot ionized gas in a cluster, they can gain energy by scattering from high-energy electrons. This changes the apparent CMB signal in the direction of the cluster, producing a spectral distortion that can be used to detect clusters across cosmic distances. In this case, the old light becomes a backlight. The photons began in the early universe, but on the way to our detectors they pass through younger structures, carrying evidence of both the beginning and the intervening growth of galaxies and clusters. Gravitational lensing also alters the CMB. As microwave photons travel through the universe, their paths are slightly deflected by the gravity of large-scale structure. Dark matter, galaxies, clusters, and filaments all contribute to this weak bending. The effect is small, but measurable in high-resolution maps. By reconstructing CMB lensing, scientists can map the distribution of matter across enormous volumes, including matter that does not shine. This turns the CMB into more than an early snapshot. It becomes a probe of the cosmic web that formed after the light was released. Ground-based observatories such as the Atacama Cosmology Telescope and the South Pole Telescope have pushed this work to smaller angular scales and higher sensitivity in selected regions of the sky. Their locations are not accidental. The Atacama Desert is high and dry, reducing atmospheric water vapor that absorbs millimeter radiation. The South Pole offers a stable, cold environment and long observing seasons over the same sky. These telescopes do not replace space missions in a simple way. They complement them, adding fine detail, improving lensing measurements, detecting galaxy clusters, and testing the same cosmological model with different instruments and observing strategies. Newer projects, including the Simons Observatory in Chile, continue that effort by building cameras with large numbers of sensitive detectors. The goal is not only to make a prettier map, it is to reduce noise, separate foregrounds, measure polarization more accurately, and search for signals that might reveal neutrino physics, inflationary physics, dark matter behavior, or subtle departures from the standard model. The more precise the map becomes, the more important systematic errors become. A tiny calibration bias, a misunderstood foreground, or a hidden instrumental effect can matter when the signal is measured in microkelvin. There is a particular humility built into CMB science. The target is everywhere, but it is not easy to see correctly. The light fills the sky, but the differences that matter are almost invisible. The map looks ancient, but every measurement is modern, passing through antennas, mirrors, cryogenic detectors, software pipelines, and human judgment. We do not hold the early universe directly. We hold records made by instruments, and we test those records until the remaining pattern is strong enough to trust. The CMB is often described as a baby picture of the universe. The phrase is useful, but incomplete. A baby picture shows a small version of something already separate from its surroundings. The cosmic microwave background is not a portrait of the universe as an object sitting in space. It is a map made from inside the universe, looking outward in every direction to the time when light last scattered. Because we are embedded in the same expanding cosmos, we see a spherical shell around us, not because we are central in a special sense, but because light from that distance has just had enough time to reach us. Every observer elsewhere in the universe would have their own CMB sky. From a distant galaxy, the surface of last scattering would be centered on that observer instead. It would overlap with ours in some regions and differ in others, depending on position and cosmic time. There is no privileged viewing platform outside the universe where the entire early cosmos can be seen at once. We make our map from one location, one galaxy, one time in cosmic history, and yet the pattern is broad enough to reveal properties of the universe as a whole. The CMB also shows a strong dipole pattern before it is removed for cosmological analysis. One side of the sky appears slightly warmer, the opposite side slightly cooler. This is mainly caused by the motion of the solar system relative to the rest frame of the CMB. Moving toward the radiation in one direction, blue shifts it slightly. Moving away, red shifts it slightly. The dipole is much stronger than the intrinsic anisotropies that cosmologists study, so it has to be subtracted. But it is itself useful because it tells us something about our motion through the large-scale universe. Once the dipole is removed and the galactic foreground is treated, the smaller temperature variations become visible. These are the ancient differences. They are not arranged in familiar constellations. They do not resemble animals or mythic figures. They do not mark a human story placed onto the sky. They are a statistical pattern. And somehow, in that pattern, there is more information about the early universe than in any simple image of a star field could provide. Statistics may sound less cinematic than a glowing nebula, but in cosmology, statistics are often where the physical story lives. A single hotspot is not enough to rewrite the model. A single cold spot may be intriguing, but it must be interpreted with care. The full distribution of spots, their sizes, correlations, polarization, and frequency behavior carry the real weight. That is why CMB papers are filled with power spectra, likelihoods, masks, covariance matrices, simulations, and uncertainty ranges. The image invites attention, but the measurements beneath it do the work. Still, some features in the CMB have attracted particular interest. There are large-scale anomalies, including alignments and asymmetries that appear unusual under the simplest statistical expectations. There is also the well-known cold spot, a region colder than average over a relatively large area. These features have been discussed for years, and some persist across datasets. But their interpretation remains unsettled. They may point to physics beyond the simplest model, or they may be statistical flukes, foreground residuals, or consequences of looking very hard at one sky when we cannot observe many independent universes for comparison. This limitation is called cosmic variance. On the largest scales, there are only so many independent patterns available in our observable universe. We cannot rerun the universe from the beginning and observe 1,000 different CMB skies to see how unusual ours truly is. For small-scale patterns, there are many samples across the sky, and statistics become stronger. For the largest patterns, the sample is limited by the size of the observable universe itself. This is one reason scientists are careful when describing anomalies. A strange feature can be real in the data without being a clear signal of new physics. The CMB asks us to accept a kind of observational loneliness. We have one sky, one ancient surface, one sequence of cosmic history leading to the place where our instruments exist. That does not make the evidence weak, but it does shape how the evidence must be handled. Cosmology is often the art of extracting reliable conclusions from a system that cannot be put in a laboratory, cannot be repeated, and cannot be viewed from outside. There are, however, many internal checks. Different missions observed the CMB with different instruments. COBE, MAP, and Planck did not have the same resolution or detector designs. Ground-based and balloon-borne experiments add independent measurements over different sky regions and angular scales. Foregrounds behave differently across frequencies. Temperature and polarization offer linked but distinct evidence. When multiple methods agree on the same broad parameters, confidence grows. Not because any single map is perfect, but because the same universe is being measured in different ways and producing a coherent picture. The coherence of that picture is remarkable. The universe appears to be about 13.8 billion years old. Its large-scale geometry is close to flat. Ordinary matter is only a small part of the total energy budget. Dark matter is a larger component, shaping structure through gravity. Dark energy dominates the current accelerated expansion. These statements are not guesses based on one image. They emerge from fitting models to CMB measurements and comparing those models with later universe observations, always with uncertainties, assumptions, and active questions attached. The age of the universe is not measured by finding the oldest star and adding a margin. It is inferred from the expansion history and the physical conditions imprinted in the CMB, combined with the model that links early and late cosmic behavior. The oldest stars and globular clusters provide important checks, but the CMB gives a deeper clock: the pattern of acoustic peaks, the density of matter and radiation, and the expansion rate together constrain the time that has passed since the hot dense phase from which the CMB emerged. The Hubble constant is one of the places where the story becomes more complicated. Measurements inferred from the early universe, including the CMB within the Standard Model, produce one value for the current expansion rate. Some measurements based on the local distance ladder, using Cepheid variables and Type Ia supernovae, produce a higher value. This difference is known as the Hubble tension. It may point to unrecognized systematic errors in one or more methods, or it may suggest that the standard cosmological model needs modification. The CMB is central to that debate because it anchors the early universe side of the comparison. A tension is not the same thing as a collapse of the model. The standard cosmological model, often called lambda CDM, fits a wide range of observations extremely well. That success makes the tensions interesting rather than dismissive. If a model failed everywhere, it would simply be replaced. If it succeeds almost everywhere but strains in a few precise places, those strains become valuable. They tell scientists where to look more carefully, where hidden assumptions may sit, and where new physics might have a chance to leave a measurable trace. The CMB has always lived between certainty and incompleteness. It gives one of the clearest views of the early universe, and at the same time it marks a boundary beyond which ordinary light cannot go. It confirms the hot early universe, yet it does not explain why there is something rather than nothing. It measures the seeds of structure, yet it does not reveal the full nature of dark matter. It supports dark energy in combination with other evidence, yet it does not tell us what dark energy is. The background is rich, but it is not the entire answer. There is another important distinction. The CMB does not come from the edge of the universe. It comes from the edge of the observable universe in the sense of looking back through light travel time. The universe may extend far beyond what we can see, perhaps enormously farther, perhaps in ways that are not directly testable. The CMB surface is simply the farthest electromagnetic surface available to us. It surrounds us in every direction because every line of sight eventually reaches the time when the universe became transparent. The distance to that surface is not as simple as saying the light traveled for 13.8 billion years. Because space expanded while the light was traveling, the matter that emitted the CMB photons is now much farther away in terms of present-day comoving distance, roughly tens of billions of light years. This is not because anything traveled through space faster than light in a local sense. It is because the metric of space expanded during the journey. Cosmological distances require definitions: light travel time, comoving distance, angular diameter distance, luminosity distance. Each answers a different question. This is where the oldest light becomes difficult to imagine. The photons reaching a detector today began moving freely when the universe was a hot young plasma, becoming transparent. Since then, they have crossed expanding space while galaxies formed, merged, burned, and changed. They passed through eras when the first stars ignited, when heavy elements spread through supernovae, when disks of gas formed around young stars, when planets condensed from dust, when Earth cooled, when oceans formed, when life began, when continents moved, when humans built antennas capable of recognizing the radiation for what it was. The photons did not know any of this. They simply traveled. A single CMB photon entering a receiver today has not carried a picture in the familiar sense. It carries a wavelength, a direction, a polarization state, an energy altered by cosmic expansion and sometimes by interactions along the way. The image appears only when countless photons are gathered, counted, compared, and placed into a map. The ancient universe becomes visible through statistics because no individual photon can tell the whole story. Detectors built for CMB work are often cooled to extremely low temperatures because their own thermal radiation would otherwise overwhelm the faint signal. Bolometers measure tiny changes in temperature as incoming radiation deposits energy. Radiometers compare signals from different parts of the sky. Superconducting transition edge sensors operate near the boundary between superconducting and normal states, where small energy inputs produce measurable changes. The engineering is not decorative. Without cold instruments, stable calibration, careful shielding, and a precise understanding of noise, the ancient background would be blurred by the equipment built to find it. Space missions also need scanning strategies. They do not simply take one snapshot and finish the job. A spacecraft like Planck spins and slowly shifts its pointing so that detectors sweep great circles across the sky. Over time, these circles overlap, allowing the same region to be measured repeatedly. Redundancy helps reveal instrument drift and systematic effects. From repeated lines of data, a full sky map is built. The finished oval is the last stage of a process that began as time-ordered measurements, voltage changes, detector responses, and pointing information. Ground telescopes face different constraints. The atmosphere emits and absorbs at microwave and millimeter wavelengths, especially when water vapor is present. Observatories are therefore placed in dry, high, cold regions when possible. The Atacama Plateau offers dry air and altitude. Antarctica offers cold stability and long viewing of the same sky. Even there, the atmosphere is not invisible. Data analysis must separate atmospheric fluctuations from celestial signals. The telescope does not only observe the universe, it observes through Earth, and Earth must be removed from the record. It is easy to forget how faint these signals are compared with ordinary experience. A human hand, a warm building, the ground under the telescope, the atmosphere above it, and the electronics inside the instrument all radiate more strongly than the variations being measured. CM science is a discipline of subtraction, shielding, cooling, comparing, and waiting. The oldest light in the universe arrives not as a spectacle, but as a slight excess power at a known wavelength, a statistical pattern that survives every serious attempt to explain it away. The blackbody nature of the CMB is one of the cleanest facts in cosmology. A blackbody spectrum has a precise shape determined by temperature. Cope's Pheris instrument measured the CMB spectrum so accurately that the match became a defining success of the hot Big Bang model. Many alternative explanations for the background struggle here, because radiation assembled from many later sources would not naturally produce such a perfect thermal spectrum. The spectrum tells us that the radiation was once in equilibrium, with matter in a hot, dense state. This does not mean every question about the early universe is solved. A blackbody spectrum tells us about thermal history, but not about the complete origin of that history. Acoustic peaks tell us about plasma conditions and cosmic geometry, but not the complete identity of dark matter. Polarization may carry traces of early physics, but foregrounds and systematics make some signals difficult to confirm. The CMB is not a magic key. It is a record, and like any ancient record, it has to be read with knowledge of the material that preserved it and the distortions it suffered on the way. Some distortions are themselves useful. The integrated Sachs-Wolf effect, for example, can slightly change CMB photon energies as they pass through gravitational potentials in a universe where those potentials evolve over time. The effect is subtle and hard to measure, but it connects the CMB to dark energy and the changing growth of structure. Reionization also leaves an imprint. When the first stars and galaxies ionized much of the intergalactic hydrogen, free electrons appeared again, scattering a fraction of CMB photons and producing large-scale polarization information about when that transformation occurred. Reionization did not erase the CMB. The universe after the first stars never returned to the dense, opaque state of its first 380,000 years. The gas was far too thin. But a small fraction of CMB photons scattered from newly freed electrons, leaving a detectable signature. In this way, the CMB contains a secondary clue from the first luminous objects. It was released before stars, but part of its pattern was lightly touched by the radiation from the earliest generations of stars and galaxies. The word surface in the surface of last scattering also deserves care. It was not a sharp shell like the surface of a planet. Recombination happened over a finite interval, so the last scattering region has thickness in time and distance. Photons last scattered at slightly different moments depending on local conditions. The CMB map is therefore a view through a thin but real cosmic layer, not a razor-thin boundary. Its thickness slightly blurs the smallest details, just as a photograph taken through mist loses fine structure. Beyond that layer lies physics that is even harder to reach. Neutrinos, which interact much more weakly than photons, decoupled earlier and should form a cosmic neutrino background, but those relic neutrinos are extraordinarily difficult to detect directly. Gravitational waves from the early universe, if they exist at detectable levels, could carry information from times far earlier than recombination. For now, the CM remains the oldest directly imaged light and the best electromagnetic window into the young universe. There is a temptation to imagine the CM as something behind the stars, a distant wallpaper at the end of space. That picture is useful only up to a point. The background is not a wall sitting beyond galaxies. It is radiation passing through the same universe the galaxies occupy. Nearby space contains CMB photons too. They pass through the room around you, through the space between planets, through interstellar gas, and through the halos of galaxies. What a CMB telescope does is measure their direction and energy well enough to reconstruct where they last scattered long ago. This means the oldest light is also local in a strange but physical sense. It is here now. It fills the space between Earth and the Moon. It passes through the solar system alongside sunlight, cosmic rays, radio transmissions, and infrared radiation from dust. Its energy density is tiny, but its presence is universal. The same radiation detected by a satellite near L2 is also passing through the space above your head. We do not notice it because our bodies are warm, our eyes are tuned to different wavelengths, and the signal belongs to instruments rather than senses. The wavelength today is in the microwave range, roughly millimeters, because the expansion of the universe stretched the original radiation by a factor of about 1100 since recombination. That factor is expressed as redshift. A photon that once had a much shorter wavelength now arrives as a microwave photon. Redshift is not simply motion through space, though motion can cause redshift too. In cosmology, it mostly records the stretching of space itself while light travels. The CMB is the most extreme everyday example of that stretching in the sky. Redshift also makes the early universe observable in a way that differs from ordinary aging. When we see a distant galaxy, its light has been stretched. When we see the CMB, the stretching is so large that a universe once glowing hot has cooled into a microwave bath. That does not mean the photons are tired in a vague sense. Their wavelengths have increased because the scale factor of the universe changed. The energy of the radiation decreased as the universe expanded, and the temperature associated with the blackbody background fell with it. This cooling shaped everything. In a hotter universe, atoms could not remain neutral. In an even hotter universe, nuclei could not remain bound. Earlier still, protons and neutrons themselves were part of a hotter particle environment. The CMB sits after several major transitions, but before the first stars. It is a boundary between a universe ruled by a dense glowing plasma and a universe where matter could begin assembling into the structures that would later become visible. The standard timeline is not guesswork arranged for storytelling. It is built from multiple forms of evidence. The CMB gives the radiation after recombination. Light element abundances test the first minutes. Particle physics constrains possible interactions. Galaxy surveys show later structure. Supernovae and baryon acoustic oscillations measure expansion history. Each piece has its own uncertainties, and some tensions remain, but the broad sequence is not arbitrary. The universe cooled as it expanded, passed through conditions that allowed nuclei, then atoms, then stars, galaxies, planets, and eventually observers capable of measuring microwave photons. The CMB is therefore a fossil, but not a fossil in stone. It is a fossil in radiation. A dinosaur bone preserves the structure of a body after minerals replace or fill what was once living tissue. The CMB preserves the structure of an early plasma through light that stopped scattering and traveled onward. Both kinds of evidence require interpretation. A fossil bone needs anatomy, geology, and dating. The CMB needs thermodynamics, relativity, plasma physics, statistics, and instrumentation. The reference to fossils is useful because the CMB also shows what no longer exists in the same form. The photon baryon plasma is gone. The surface of last scattering is not an object we could visit because the matter that emitted those photons evolved, collapsed, formed structures, and moved with cosmic expansion. The ancient state has vanished, but the radiation remains. It is the trace of a condition that filled all space and then changed forever. If you take the CMB seriously, the night sky becomes only the recent chapter. Stars dominate human vision because they are bright at optical wavelengths and close enough to stand out. Galaxies appear as deep field islands of light. Nebulae glow where gas is heated or illuminated. But behind that visible architecture is an older radiation field that predates all of it. The oldest light does not compete with the stars in brightness or beauty. It outlasts them as evidence. Our Sun is about 4.6 billion years old. The Milky Way's oldest stars are much older, more than 13 billion years in some cases. But the CMB is older still. Not in the sense that the photons existed unaltered from the first instant, but in the sense that the light we observe last interacted with ordinary matter when the universe was only about 380,000 years old. The photons have been stretched and affected by later structures, but their origin as freely traveling radiation belongs to a time earlier than any star we can see. There is a quiet difference between looking at a star and measuring the background. A star is an object with a surface, a core, a life cycle, and a location. It has fusion, magnetic fields, wind, and age. The CMB is not like that. It is a condition of the whole observable universe arriving from the past. It does not have a single place because the early plasma had no single place. It was the universe itself in a state from which all later luminous objects would emerge. When CM scientists remove foregrounds, they are not trying to make the universe simpler than it is. They are separating layers of history. The Milky Way is a middle-aged galaxy with dust lanes, star-forming regions, supernova remnants, and magnetic fields. Extragalactic sources add their own emission. Galaxy clusters distort the signal. The solar system contributes small foregrounds in some contexts. Behind and among these layers is the microwave background. A clean map requires knowing enough about the younger universe to subtract it without accidentally subtracting the ancient one. That subtraction is one reason independent datasets matter. A feature that appears in one frequency but not another may be foreground. A pattern that changes when a galactic mask is altered may be suspect. A signal that appears in temperature but not in the expected polarization pattern may require caution. A result that survives different instruments, sky cuts, pipelines, and statistical tests becomes more persuasive. The CMB does not surrender its meaning just because someone points a telescope at it. The meaning comes from consistency under pressure. The universe revealed by the CMB is both simple and strange. Simple because a small set of parameters can describe much of the observed pattern. Strange because those parameters imply a cosmos dominated by components we do not directly see: dark matter and dark energy. Ordinary atoms, the material of mountains, oceans, atmospheres, cells, stars, and planets, are not the main substance of the universe. The CMB did not create that conclusion alone, but it helped make it quantitatively precise. Ordinary matter leaves its marks through acoustic oscillations and through the later formation of stars and gas. Dark matter leaves its marks through gravity, shaping the wells into which ordinary matter falls. Radiation leaves its mark through pressure, temperature, and the expansion history. Dark energy leaves its mark mostly through late-time expansion and the geometry inferred when CMB measurements are combined with other data. Each component is inferred by how the universe behaves, not by how satisfying the categories feel. This is one of the reasons the CMB feels less like an answer than a measured beginning. It tells us the universe was once hotter, denser, smoother, and simpler in composition. It tells us the later complexity had roots in tiny differences. It tells us our galaxy belongs to a much larger pattern, but it also points to the parts of the model that are still named more by their effects than by their nature. There are also questions about the earliest moments that the CMB can approach only indirectly. Inflation, if it occurred, would have happened long before recombination. Its strongest possible trace in the CMB would be the pattern, scale dependence, and statistical properties of primordial fluctuations, and perhaps a primordial B-mode polarization signal. Current observations strongly constrain many possibilities, but they do not identify the mechanism with finality. The CMB narrows the field. It does not yet reveal the engine. The first fractions of a second remain among the hardest places in science to speak about responsibly. Energies were far beyond anything we can reproduce directly. Theories become mathematical extensions tested by their consequences rather than by direct recreation. Words like beginning, origin, and before can become misleading if used carelessly. The CMB gives a firm observational surface at 380,000 years, and from that surface scientists infer earlier conditions. The farther back the inference goes, the more carefully it has to be handled. There may be gravitational waves from the early universe crossing space today, just as the CMB does. If detected in the right way, they could open a window behind the light barrier, because gravitational waves interact so weakly with matter that they could travel from much earlier times. But detecting a primordial gravitational wave background is extraordinarily difficult. Astrophysical foregrounds, instrumental limits, and galactic emission all complicate the search. For now, the CMB remains the oldest light, while the hope for older messengers continues. The CMB also helps constrain neutrinos. These light, weakly interacting particles affect the expansion rate and the growth of structure. The early universe was full of them, and their collective influence changes the CMB pattern in subtle ways. Later, CMB lensing and galaxy surveys can constrain the sum of neutrino masses because massive neutrinos suppress structure growth on certain scales. This means the oldest light is also connected to some of the smallest known particles, linking cosmology to particle physics across an enormous range of scale. No laboratory on Earth can build a universe, but the universe itself has run experiments under conditions we can no longer access. The CMB is one of the readouts. It contains information about sound waves in plasma, the density of matter, the behavior of radiation, and the geometry of space. It is a sky-sized instrument left by nature, though nature did not intend it as one. Human instruments only learned how to read the trace. The history of reading that trace is also a history of increasing resolution. Penzias and Wilson found the background as an almost uniform excess. Kobe confirmed the blackbody spectrum and revealed the first broad anisotropy map. UMAP sharpened the pattern and improved cosmological parameters. Planck added greater detail, wider frequency coverage, and more precise component separation. Ground-based telescopes then pushed into small-scale temperature, polarization, lensing, and cluster science. The same ancient light has been revisited again and again, not because the first detection was doubtful, but because each improvement extracts a different layer of information. If the Kobe map is like seeing a coastline through fog, Planck is like seeing the same coast with bays, inlets, and ridges resolved more clearly. The analogy is imperfect, because the CMB is not a landscape, but the progression matters. Better resolution reveals smaller angular scales, and smaller scales correspond to physical processes with different histories. Damping at small scales, sometimes called silk damping, shows how photon diffusion smoothed out fluctuations below certain sizes in the early plasma. Even the disappearance of detail becomes information. Silk damping occurs because photons wandering through the plasma before recombination could diffuse out of small overdense regions, carrying energy with them and smoothing fluctuations on small scales. The result is a decline in power at high multipoles in the CMB spectrum. This is not a failure of the map, it is a physical imprint of how the early universe behaved before it became transparent. The ancient light does not preserve every detail, it preserves the details that survived the physics of the plasma. Another measured feature is the ratio of temperature to polarization signals and their correlations. These correlations test whether the same acoustic physics is being seen in different ways. Temperature tells where regions were hotter or colder. Polarization tells about the local radiation field at scattering. When the two agree in the expected pattern, confidence in the model deepens. It is harder for a foreground or an instrumental artifact to imitate all of the linked signatures across multiple frequencies, angular scales, and experiments. The CMB also reminds us that the universe was not built with human categories in mind. We separate matter, radiation, dark matter, dark energy, and curvature, because those categories work in equations and observations. The early universe did not label itself. It evolved according to physical relationships. Our models are maps, not the territory. They are judged by how well they predict, connect, and survive measurement. The CMB is one of the strictest tests those maps must pass. On a computer screen, the Planck map can be opened like any other image file. It can be downloaded, projected, cropped, colored, and placed beside other astronomical maps. That accessibility can make it seem ordinary. But the file represents years of spacecraft operation, instrument cooling, sky scanning, calibration, foreground modeling, statistical analysis, and comparison with theory. Inside an image that fits on a monitor is a measurement of the observable universe before it contained a single star. The word observable is doing important work. The entire universe may be larger than the observable universe, possibly much larger. The CMB cannot tell us everything beyond our horizon because information from those regions has not reached us. But the uniformity of the CMB across widely separated directions raises its own puzzle. Regions on opposite sides of the sky appear to have nearly the same temperature, even though, in a simple non-inflationary picture, they would not have had time to exchange information before recombination. Inflation was proposed in part to solve this horizon problem by making the observable universe grow from a region that had once been in causal contact. Inflation also addresses the flatness problem, the question of why the universe appears so close to spatially flat rather than strongly curved. Rapid early expansion would flatten curvature much as inflating a balloon makes a small patch appear flatter. It could also stretch quantum fluctuations to cosmic scales, providing seeds for structure. These are strong motivations, not final proof of a specific model. Many inflationary models exist, and not all survive observational constraints. The CMB helps eliminate some and favor broad features, but the detailed physics remains under investigation. The search for primordial non-Gaussianity is one example. If early fluctuations were purely random in the simplest inflationary way, their statistics should be close to Gaussian, meaning their distribution follows a particular mathematical form. Deviations could hint at interactions or mechanisms beyond the simplest models. Planck found the fluctuations to be very close to Gaussian overall, placing tight limits on many alternatives. Once again, the absence of a dramatic anomaly is not empty. It is a measurement that tells theorists what the early universe did not do, or at least did not do strongly enough to leave a detectable mark. Science often advances through exclusions. A map says yes to some possibilities and no to others. The CMB says the early universe was nearly uniform, but not perfectly so. It says the fluctuations were nearly scale invariant, but not exactly. It says the geometry is close to flat. It says ordinary matter cannot account for the gravitational behavior. It says the radiation was thermal. Each statement narrows the darkness around the beginning without pretending that the darkness has disappeared. The near-scale invariance of the primordial fluctuations means that variations had similar strength across a wide range of sizes, with a slight tilt. That tilt, measured through the scalar spectral index, is one of the pieces of evidence relevant to inflationary theory. A perfectly scale-invariant spectrum would have one value. Observations show a small departure. The difference is technical, but it matters. The early universe was not arbitrary. Its pattern has a measurable shape, and that shape reaches across the largest structures we observe today. Temperature maps are usually shown with the Milky Way removed, but if you look at raw microwave sky maps, the galaxy dominates many views. This is not surprising. We live inside a spiral galaxy full of material. Dust grains absorb starlight and re-emit energy in the infrared and microwave. Electrons interacting with magnetic fields produce synchrotron radiation. Ionized gas emits free radiation. The foreground is not an annoyance from outside astronomy. It is astronomy of a younger layer, overlapping the ancient one. Component separation is therefore a delicate process. If too much is removed, genuine CMB signal could be distorted. If too little is removed, galactic emission could masquerade as cosmology. Different teams use different methods, such as internal linear combinations, template fitting, parametric modeling, and independent component analysis. Agreement between methods is important. Disagreement is also useful, because it reveals where assumptions matter most. The final confidence comes not from making one perfect map, but from understanding how imperfect maps converge. A laboratory comparison helps. Imagine trying to hear a low, steady note played in a building full of machines. Some machines hum at known frequencies, others change with temperature. Some vibrations come through the floor. The note is everywhere, but faint. You record from many places, subtract what you understand, compare channels, and ask what remains. CM work is not exactly sound, but the logic is similar. The ancient signal is extracted from a world that is also making its own microwave noise. The result, when it holds, is extraordinary. We can say that small density differences existed before the first stars. We can say that the later universe did not begin from a perfectly smooth state. We can say that the cosmic web had measurable roots in a plasma older than every galaxy. The map is not a mythic memory, it is a measurement, and the measurement is enough. The first galaxies amplified those early differences through ordinary gravity. Dark matter halos collapsed and merged, gas cooled, fell inward, and formed stars. Supernovae enriched their surroundings with heavier elements. Black holes formed from collapsed stars, and perhaps other channels, then grew through accretion and mergers. Galaxy disks settled. Elliptical galaxies assembled through violent histories. None of this is visible in the CMB directly, but the large-scale arrangement of later matter can be compared with the initial pattern that the CMB records. Baryon acoustic oscillations provide another bridge. The same sound waves that left peaks in the CMB also left a preferred scale in the later distribution of matter. Galaxies are very slightly more likely to be separated by a certain characteristic distance because of those early acoustic waves. Galaxy surveys can measure this scale at different cosmic times, using it as a standard ruler to study expansion history. The CMB calibrates the ruler in the early universe. The galaxies show how it appears later. This connection is one reason the CMB is not isolated from the rest of astronomy. It links to galaxy redshift surveys, supernova distances, gravitational lensing, cluster counts, and the distribution of intergalactic gas. A microwave map becomes part of a larger network of evidence. If one part of the network shifts, the others must be checked. Cosmology is not a single pillar, but a structure of comparisons, and the CMB is one of the deepest foundations. The CMB temperature also changes with redshift. In the past, when the universe was smaller, the background was hotter. At recombination, it was about 3000 Kelvin. Later, as space expanded, it cooled toward its current 2.7 Kelvin. Observations of molecules and gas in distant systems can test this temperature evolution at intermediate redshifts. The expected relationship is simple in the standard model, but testing it matters because assumptions about expansion and radiation should be checked whenever observations allow. The universe cooled, but not into stillness. It cooled into structure. The background faded from visible brilliance into microwaves, while gravity gathered matter into stars. The same expansion that stretched the light also created time for complexity to develop. The CMB is therefore both an afterglow and a clock, not with hands and numbers, but with a spectrum, a temperature, a redshift, and a pattern of fluctuations. If human eyes could see microwaves with enough sensitivity, the sky would look very different. The stars would not dominate in the same way. A nearly uniform glow would cover everything, with tiny variations far below natural visual contrast. But human biology is not built for that. We see a narrow range of wavelengths shaped by the sun's output and Earth's atmosphere. To see the CMB, we had to build senses outside ourselves: antennas, cryogenic detectors, satellites, and computational tools capable of measuring what vision cannot. This is a recurring theme in astronomy. The universe is not limited to what human eyes can see. Radio maps reveal jets and cold gas. Infrared telescopes see through dust and find redshifted galaxies. X-ray observatories trace hot plasma around black holes and clusters. Gravitational wave detectors measure space-time distortions from merging compact objects. The CMB belongs to this expanded sensory world, a signal that was present long before humans knew how to receive it. The Bell Labs horn antenna did not look like a portal into cosmic history. It was a metal structure built for radio work, practical and specific. COBE did not look like a mythic vessel. It was a satellite with instruments, shielding, telemetry, and mission constraints. Planck was a spacecraft with a telescope, cryogenic systems, detectors, and a finite observing lifetime. The oldest light reached all of them, but only careful design allowed it to become evidence rather than background. There is a lesson here, though not a motivational one. The universe can be obvious and hidden at the same time. The CMB fills all space, yet it took theoretical prediction, engineering, accidental detection, and decades of refinement to understand it. It was not hidden because it was rare. It was hidden because the right question and the right instrument had not yet been brought together. Many parts of the universe may be like that: present, physical, measurable, but waiting for the correct way to ask. The CMB also shows how science handles the unseen. No one watches dark matter particles form halos in a direct photograph. No one photographs inflation directly. No one sees recombination as a local event happening now. Instead, scientists infer from linked evidence. The inference is not arbitrary. It is constrained by equations, observations, and failed alternatives. The strength of a scientific model lies not in how dramatic it sounds, but in how many independent facts it can explain without breaking others. Consider the ordinary hydrogen atom. It is simple by everyday standards: one proton, one electron. But the moment hydrogen became stable across the universe, changed what light could do. Before neutral atoms formed, free electrons kept photons trapped. After they formed, the photons moved. The formation of neutral hydrogen did not create stars, planets, or life immediately. It created transparency, and transparency allowed the universe to leave a visible record of its own youth. That transparency did not mean the universe became easy to understand. Neutral hydrogen can absorb and emit radiation at specific wavelengths, including the 21-centimeter line, which astronomers hope to use to study the Dark Ages and cosmic dawn. This line could eventually map eras after the CMB, but before ordinary galaxies became abundant enough to see easily. The observations are difficult because the signal is faint and foregrounds are strong. But the goal shows how the CMB is one boundary in a larger effort to fill the gap between recombination and the first luminous structures. Between the CMB and the first galaxies lies a long stretch of cosmic history that remains partly hidden. It is not empty time. Gas-cooled. Dark matter halos grew. The first dense pockets formed. But without many bright sources, direct observation is difficult. The oldest light tells us where that era began. The most distant galaxies and possible 21-centimeter signals tell us where it was heading. The space between them is one of the great unfinished maps of cosmology. Telescopes like the James Webb Space Telescope do not see the CMB, but they do extend the story that begins with it. By observing infrared light from very distant galaxies, they look into the first few 100 million years of star and galaxy formation. These galaxies are younger than the CMB by cosmic standards, but still ancient compared with Earth. Their abundance, brightness, and masses test models of early structure formation. If the universe formed galaxies faster than expected, the initial conditions from the CMB and the physics of gas, stars, and dark matter must all be examined carefully. Early galaxy observations do not replace the CMB. They depend on it. Cosmological distances, ages, and growth histories are interpreted within a framework anchored partly by the microwave background. The CMB sets the initial conditions. The galaxies show later outcomes. When the outcomes appear surprising, the question becomes whether astrophysics within galaxies is more efficient than expected, whether observations are being misread, whether sample sizes are biased, or whether deeper cosmological assumptions need revision. This is why the oldest light remains alive in current research. It is not an old discovery filed away in textbooks. It is used whenever a new survey measures structure, whenever a new telescope finds early galaxies, whenever a local expansion measurement sharpens the Hubble tension, whenever a CMB polarization experiment searches for primordial B modes. The light is ancient, but the questions attached to it keep changing. A processed CMB map often uses red and blue to show warmer and cooler regions. The average has been removed, the dipole has been removed, and foregrounds have been modeled away. What remains is exaggerated visually so the pattern can be seen. The actual temperature differences are tiny. A red region might be only tens or hundreds of microkelvin warmer than average. A blue region might be similarly cooler. Without the color scale, the background would look almost perfectly even. The relationship between temperature and density in the CMB is subtle. A warm spot does not simply mean a dense spot in a direct, everyday way. Gravitational redshift, photon pressure, baryon velocity, density contrast, and other effects all contribute to the observed anisotropy. The Sachs-Wolf effect, Doppler effects, acoustic oscillations, and later integrated effects are part of the full interpretation. This is why the map is not read like a weather map. It is read through a physical model of the early universe. Still, the broad meaning remains powerful. The universe had structure in embryo. It had places where gravity would later gain a slight advantage. It had a pattern that was nearly uniform, but not featureless. From those differences came everything that required unevenness: galaxies, stars, planets, and the chemical environments where life could eventually appear. If the CMB had been perfectly smooth, the later universe would not resemble the one around us. The amplitude of the fluctuations had to be just right in a broad sense. Too small and structure might form too slowly or not at all on useful scales. Too large, and the early universe would become too clumpy too quickly, producing a very different cosmic history. This kind of statement can easily be overused philosophically, but it is physically meaningful. The observed fluctuation amplitude is one of the parameters that governs how structure grows, and it is measured with high precision from the CMB and other data. There is no need to turn that into destiny. The universe did not arrange itself for us in any simple scientific statement. The CMB tells us what the initial conditions were in our observable region. From those conditions, under known and partly unknown physics, the later universe developed. The fact that we are here to measure the background is a consequence of that history, not an explanation for it. The cosmic microwave background also gives a way to test the number of relativistic particle species in the early universe, often expressed through the effective number of neutrino species. Additional light particles would change the expansion rate and leave marks in the CM power spectrum. Observations so far are broadly consistent with the known neutrino picture, though measurements continue to improve. This is another example of the CMB acting as a particle physics detector on cosmic scales. The early universe was a place where the very large and the very small were inseparable. Quantum fluctuations may have seeded cosmic structure. Particle species affected expansion. Atomic physics determined recombination. Gravitational growth shaped galaxies. Radiation pressure drove acoustic waves. A microwave photon entering a detector today carries the consequences of all those scales blended together, from quantum fields to galaxy clusters. The language of place becomes difficult here. The early universe was not a point somewhere far away. It was every place, including the matter that would one day become the region around the Milky Way. When we look at the CMB, we see distant matter as it was when it released the light now reaching us. But the matter that was here also released CMB photons, and those photons have long since traveled away to other regions. Every observer receives ancient light from elsewhere and sends their own region's ancient light beyond reach. This is one of the quietest scale changes in cosmology. The CMB is both around us and from far away. It fills local space, but each photon we measure last scattered in a region now extremely distant. The early universe was everywhere, and the present universe is the expanded result of that everywhere changing. Human language was not built for that geometry. The mathematics handles it better than intuition does. Astronomers often use maps in galactic coordinates, with the plane of the Milky Way running across the middle. This is useful because our galaxy is a dominant foreground. But the CMB itself is cosmological, not galactic. After foreground removal, its statistical pattern should not care about the Milky Way's disk. Any correlation with galactic structure is therefore suspicious and must be checked. This is one reason masks, frequency comparisons, and simulations are central to CMB analysis. Calibration is another quiet but essential part of the story. An instrument measuring microkelvin differences must know its own gain, beam shape, pointing, thermal stability, and response over time. A small beam asymmetry can affect maps. A tiny temperature drift can mimic a sky signal. Cosmic rays can disturb detectors. The final cosmological parameters depend on countless engineering details that never appear in popular images but determine whether the image can be trusted. Behind every CMB map is a log of problems solved, heaters monitored, detectors flagged, timelines cleaned, noise models revised, beams measured with planets, foreground templates compared, software checked by independent groups. The work is slow because the signal is old and faint. Mars or Jupiter may pass through a detector's beam not as the main target, but as a calibration source, a bright known object helping scientists understand the instrument that is trying to measure ancient radiation. The planets of our own solar system, then, become tools for reading the early universe. A spacecraft can use a planet to calibrate a beam. A telescope can use known sources to test pointing. The moon, the atmosphere, the ground, and the galaxy can all be obstacles or references depending on context. Cosmology is not detached from the nearby universe. It depends on understanding the local environment well enough to subtract it or use it. Even the color palettes used in CMB images require care. The red and blue colors are not literal. They are chosen to represent small positive and negative deviations from an average temperature. Different maps may use different smoothing, different masks, and different component separation methods. A public image can communicate the existence of structure, but scientific conclusions come from the underlying calibrated data and the statistical tools applied to it. This matters because images can become too familiar. The Planck oval appears in articles, classrooms, documentaries, and lectures until it risks becoming a symbol rather than a measurement. But it is not a logo for the Big Bang. It is data from microwave detectors, processed into a map of temperature fluctuations. Treating it as evidence means remembering how it was made and what it can and cannot say. What it can say is extraordinary enough. The universe was hot and dense. It became transparent after about 380,000 years. Its radiation has cooled to about 2.7 Kelvin. It contains tiny anisotropies at the level of about 1 part in 100,000. Those anisotropies match a pattern expected from acoustic oscillations in the early plasma. Combined with other observations, the CMB supports a universe about 13.8 billion years old, dominated today by dark energy, with dark matter outweighing ordinary matter. What it cannot say is equally important. It cannot show the literal first instant. It cannot identify the dark matter particle. It cannot by itself solve the Hubble tension. It cannot tell us whether the universe beyond our observable horizon is finite or infinite. It cannot prove every detail of inflation. A good map has edges, not because the universe necessarily ends there, but because measurement has limits. Those limits are not discouraging. They are the reason the CMB remains scientifically active. A completed answer would not require new telescopes in Chile, Antarctica, balloons, or future satellites. Yet new instruments are being built because there are still weaker signals to measure and sharper tests to run. Semblensing, polarization, foreground science, neutrino mass, dark radiation, primordial gravitational waves, cluster catalogs, and small-scale anisotropies all keep the old photons at the center of new work. The South Pole Telescope, with its large dish and millimeter wave cameras, surveys the microwave sky from Antarctica. The Atacama Cosmology Telescope observed from the high Chilean desert. The Simons Observatory is designed to map the millimeter sky with high sensitivity. Other experiments, including balloon missions and specialized polarization instruments, focus on particular scales or signals. Each experiment has strengths and weaknesses. Some see large areas, some see small details, some measure temperature best, some are built to chase polarization. The full picture grows by combining them. A telescope at the South Pole watching the oldest light is a strange image only until the practical reasons become clear. The air is dry and cold. The sky can be monitored for long periods. Human presence is difficult, but the observing conditions are valuable. In one of the harshest environments on Earth, instruments measure radiation from a time when Earth did not exist, when the atoms that would become Antarctica had not yet been forged in stars. The Atacama site offers a different version of the same pursuit. High altitude, dry atmosphere, and wide sky access make it one of the best places on Earth for millimeter astronomy. Telescopes there do not see the CMB alone. They also observe dusty galaxies, galaxy clusters, and other sources that share the same wavelengths. The difficulty is part of the value. Separating the old background from newer signals forces a more complete understanding of the millimeter sky. Future CMB measurements may become precise enough to reveal subtle departures from current expectations, or they may tighten the model further. Both outcomes matter. A surprise could open new physics. A stronger confirmation could close off theories that once seemed possible. In science, not finding a hoped-for signal is not the same as finding nothing. It can be a boundary placed around nature, a statement that certain things, if they exist, must be weaker, rarer, or different than predicted. The CMB has already done this many times. It has limited curvature. It has constrained extra-relativistic particles. It has constrained primordial non-Gaussianity. It has shaped inflationary model building. It has measured the baryon density in a way that agrees with light element evidence. It has supported dark matter as a necessary gravitational component. The oldest light has become one of the strictest editors of cosmological imagination. Cosmology before the CMB was not empty of evidence, but the background changed the field's character. It gave scientists a relic that came from the early universe itself. Later, Cobb's blackbody measurement and anisotropy detection made the relic detailed. Map and Planck made it precise. The subject moved from broad argument to high-precision measurement, where competing models could be tested against numbers rather than only general ideas. The discovery also changed the emotional scale of the sky. The darkness between stars is not simply absence. It contains radiation from the early universe, too faint for eyes, but measurable everywhere. A patch of sky that seems empty in visible light is not empty to a microwave detector. It carries the same background pattern, the same ancient temperature, the same evidence that the visible universe emerged from a hot, dense state. Still, it is important not to say the CMB is the echo of an explosion in ordinary space. The Big Bang was not an explosion from a point into emptiness. It was an expansion of space from an earlier hot, dense state. Every region of the observable universe was once part of that state. The CMB is not shrapnel flying away from a center. It is radiation from the time when the expanding universe became transparent. Misleading images are hard to avoid because human imagination likes centers, edges, and outside viewpoints. Cosmology often denies those conveniences. There is no known central point of expansion. Every distant galaxy appears, on large scales, to recede as space expands. Every observer would see a CMB surrounding them. The oldest light teaches a geometry in which the observer is local, not central, and the past surrounds every line of sight. The mathematical framework behind this is general relativity, which treats gravity not as a simple force acting in fixed space, but as the curvature and dynamics of spacetime. The expanding universe is described by solutions in which distances between large-scale comoving points grow over time. The CMB fits into that framework as radiation whose wavelength stretches with the scale factor. Its temperature falls as the universe expands. Its pattern records early density variations evolving under relativistic cosmology. That might sound remote from the physical map, but it is what allows the map to become a measurement of cosmic parameters. Without a model of expansion, redshift, gravity, and plasma physics, the CMB would be a strange glow with a pattern. With the model, it becomes a way to estimate the contents and history of the universe. If the model changes, the interpretation changes too, which is why tensions and anomalies receive so much attention. The model most often used is called lambda CDM. Lambda represents the cosmological constant or dark energy, like component-driving accelerated expansion. CDM stands for cold dark matter, meaning dark matter that moved slowly compared with light when structure formed. The model is simple compared with the universe itself, using a small set of parameters to explain a vast range of observations. Its success is impressive. Its unknown components are a reminder that success and completeness are not the same. A map can be accurate and still incomplete. Ancient sailors used coastlines before they knew plate tectonics. Astronomers used planetary motions before gravity was understood in its modern form. Cosmologists use lambda CDM because it works extraordinarily well, while also recognizing that dark matter and dark energy require deeper explanation. The CMB is not the end of cosmology. It is the evidence any deeper theory must still explain. The oldest light also carries a kind of silence about everything human. When it began traveling, there were no planets with oceans, no continents, no atmospheres like ours, no biology, No eyes, no names for stars. The universe was not waiting for those things. It was cooling, expanding, and letting small differences grow. The background radiation crossed time while generations of stars later formed and died, producing the elements from which rocky worlds and living chemistry would eventually be assembled. Heavy elements came later. Carbon, oxygen, silicon, iron, and many other elements were built in stars and stellar explosions after the CMB had already been released. The early universe was chemically simple, mostly hydrogen and helium by mass, with traces of other light nuclei. This means the CMB belongs to a cosmos before geology, before dust-rich planet formation, before the periodic table became populated by stellar evolution. It is light from a universe not yet capable of making worlds like Earth. That makes the CMB more than a cosmological datum. It is a reminder that complexity has a history. The atoms in a telescope mirror and the silicon in a detector did not exist when the CMB was released. They were made later by stars, scattered into interstellar space, gathered into new systems, and eventually shaped by humans into instruments that could measure radiation older than the atoms in the instruments themselves. The detector is younger than the light by almost the entire age of the universe. This kind of reflection can become too poetic if pushed too far, but the factual point remains. The CMB predates the heavy element universe. It predates galaxies as stable systems. It predates the astrophysical environments that made observers possible. When we measure it, the later universe is using its own products to examine an earlier state in which those products had not yet appeared. The radiation field also sets a temperature floor that mattered more in the distant past. Today, the CMB is so cold that many astrophysical environments are warmer, but at high redshift, the background temperature was higher. Early gas clouds and dust grains existed in a warmer radiation bath. This affects cooling, chemistry, and the interpretation of distant observations. The CMB is not only a relic seen from afar, its changing temperature was part of the environment through which cosmic structure formed. For very distant galaxies, the CMB can influence observations by heating dust slightly or reducing contrast between cold dust and the background. These effects are technical but real, and they grow more important at high redshift. As astronomers push deeper into cosmic dawn, they must account for the background not merely as an ancient signal, but as a physical radiation field present around the objects being studied. The old light is therefore woven through astronomy in quiet ways. It defines a background for microwave observations. It calibrates cosmology. It constrains particle physics. It backlights galaxy clusters. It is lensed by dark matter. It sets a temperature that changes with redshift. It marks the beginning of transparency. Few signals in science are so faint in everyday terms and so central in meaning. The CMB is also a reminder of how much information can be stored in small deviations. A difference of microkelvin across the sky may seem negligible compared with the heat of a star or the temperature of a planet, but on cosmological scales, those deviations are the imprint of gravity, sound waves, and density contrasts in the early universe. The later universe grew from differences small enough that only precision instruments could find their ancestors. The largest structures today, galaxy clusters and superclusters, did not form as bound objects in the early plasma. Their initial regions were only slightly denser than average. Over time, dark matter gravity amplified them. Ordinary matter fell in, heated, cooled, formed stars, and sometimes was expelled by feedback. The CMB shows the early smoothness. Later surveys show the grown structure. The transformation between them is the long work of gravity in an expanding universe. Gravity is patient in cosmology. It does not need the universe to be highly uneven at the beginning. It only needs slight advantages and enough time. A region a little denser than its surroundings pulls a little more matter. That makes it denser still. Expansion resists collapse on large scales. Radiation pressure mattered early, and dark energy matters later, but gravity keeps working wherever matter can gather. The CMB gives us the initial unevenness from which that patient process began. This is why the map can feel calm rather than violent. It is not a picture of explosions tearing through space. It is a picture of small differences that became significant because the universe was old enough for them to grow. The drama is not a single impact or burst. It is accumulation. Tiny fluctuations, repeated across the sky, carried through billions of years of expansion and collapse, became the scaffolding for everything visible. In the CMB, hot and cold spots are correlated across scales in ways that can be measured precisely. These correlations are not arbitrary artistic texture. They are what allow cosmologists to estimate parameters. The amount of matter affects peak positions and heights. The baryon density changes odd and even peaks. The dark matter density changes the timing of equality between matter and radiation. The thickness of last scattering, diffusion damping, reionization optical depth, and lensing all leave their own traces. The parameter called optical depth to reionization tells how much scattering occurred after the first stars and galaxies ionized intergalactic gas. It is measured partly through large-scale polarization, which is difficult because those angular scales are vulnerable to foregrounds and systematics. Improved polarization measurements refine the timeline of reionization and influence estimates of other parameters, such as the amplitude of primordial fluctuations. A small uncertainty in one early quantity can ripple through the model. This interdependence makes CMB analysis a careful balancing act. Parameters are not always measured independently. Changing one can affect the best fit value of another. Scientists use likelihood methods, statistical sampling, and combinations with other datasets to find ranges that fit the observations. The final numbers may look clean in a table, but behind them is a landscape of correlations, assumptions, priors, and tests. The public often sees the answer. Researchers live with the uncertainty. Error bars are not decoration. They are part of the measurement. A value without an uncertainty is incomplete. In cosmology, where one sky must stand in for the observable universe, honesty about uncertainty is not a weakness. It is one of the ways the field stays connected to reality. Some uncertainties shrink with better instruments. Detector noise can be reduced. Frequency coverage can improve foreground separation. Larger sky coverage can reduce sample variance on intermediate scales. Better beams can resolve smaller features. Other limits are harder. Cosmic variance on the largest scales cannot be beaten by building a more sensitive detector, because the limitation is not noise in the instrument, it is the finite number of large-scale modes in our observable universe. That limit is strangely final. There are questions about the largest CMB patterns that may never become as precise as questions about smaller scales. We can improve foreground modeling and polarization measurements, but we cannot observe a second independent observable universe. The largest features may always carry a little more ambiguity, not because scientists are careless, but because the universe gives only one sample at that size. The smaller scales, by contrast, continue to open. High-resolution CMB measurements reveal lensing, cluster effects, point sources, dusty galaxies, and damping physics. These are not all primordial signals, but they are part of the microwave sky. The more sensitive telescopes become, the more the CMB becomes intertwined with the astrophysics of galaxies and clusters. The old light is increasingly used to study the younger universe through which it passed. A photon that last scattered from the early plasma may pass near a galaxy cluster billions of years later. The hot gas in that cluster may boost its energy slightly. The cluster's gravity may bend its path. Dusty galaxies behind or within the same region may add foreground emission. Then the photon reaches a detector on or near Earth, where it is counted as part of a map. Its journey is ancient, but not untouched. This is one reason scientists distinguish primary anisotropies from secondary anisotropies. Primary anisotropies were imprinted at or before last scattering. Secondary anisotropies arise as photons travel through evolving structure. Both are valuable, but they answer different questions. Confusing them would blur the story. Separating them allows the CMB to speak both about the early universe and about the later growth of matter. The thermal Sunyaev-Zeldovich effect is one secondary signal. The kinetic Sunyaev-Zeldovich effect, caused by the motion of ionized gas relative to the CMB rest frame, is another. Gravitational lensing is another. The integrated Sachs-Wolfe effect is another. These effects are subtle, but together they turn the background into a screen on which the intervening universe leaves fingerprints. It is easy to imagine ancient light as pristine, but the more useful picture is more complex. The CMB began as a clean relic of recombination. Then, it crossed a universe that became clumpy, ionized, magnetized, dusty, and filled with galaxies. By the time it arrives, its primordial pattern is still there, but layered with later information. The task is not simply to preserve purity, it is to understand the layers. Understanding layers is also how cosmologists compare the CMB with maps of galaxies. A gravitational lensing map reconstructed from CMB distortions traces integrated matter along the line of sight. Galaxy surveys trace luminous or selected matter at particular redshifts. Weak lensing surveys trace matter through distortions in galaxy shapes. Each method has biases and systematics. Agreement strengthens the model. Disagreement may reveal measurement problems, astrophysical complications, or new physics. The so-called S8 tension, involving the amplitude of matter clustering inferred from some late universe surveys compared with early universe predictions, is one example of an active comparison. It is less famous than the Hubble tension, but important. Some surveys find slightly lower clustering than expected from the Planck-based lambda CDM model. The statistical significance depends on datasets and assumptions, so the result is not a simple contradiction. It is a pressure point where better measurements are needed. The CMB sits at the beginning of these pressure points. If the early universe parameters are right, then late universe observations should grow from them under the assumed physics. If late structure appears different, something in the chain may need adjustment. That chain is long: primordial fluctuations, dark matter behavior, baryonic physics, galaxy formation, feedback, lensing calibration, survey selection, and cosmic expansion. The oldest light starts the calculation, but it does not control every later complexity alone. This is why cautious language matters. Scientists do not say a tension proves new physics as soon as it appears. They ask whether instruments are calibrated, whether samples are biased, whether foregrounds are understood, whether simulations include the relevant astrophysics, whether statistical methods agree. The universe is difficult enough without adding certainty where none has been earned. The cosmic microwave background rewards patience. Its discovery took theory and accident. Its first anisotropy map took a satellite. Its precision required decades. Its polarization continues to demand better instruments and foreground models. The signal itself has been traveling for nearly the entire history of the universe. Human impatience is the short-lived thing in this story. The timeline from the CMB to now can be compressed into a sequence, but the compression hides the scale. First, the universe becomes transparent. Then dark ages. Then first stars. Then early galaxies. Then reionization. Then larger galaxies assemble. Then clusters grow. Then the solar system forms. Then Earth evolves life. Then intelligence builds radio receivers. On paper, it looks orderly. In cosmic time, each step contains vast internal histories. The first stars may have been massive and short-lived, producing ultraviolet radiation and the first heavy elements. They're supernovae, enriched gas, that later formed new generations of stars. Galaxies grew through mergers and accretion. Black holes formed and fed. Feedback from stars and active galactic nuclei heated and expelled gas. The CMB does not describe these processes directly, but it gives the initial field from which their environments emerged. The Milky Way itself is a late product of this growth. Its halo, disk, bulge, satellite galaxies, streams, gas clouds, and central black hole all belong to a universe that had already been developing for billions of years. Some of its oldest stars formed from gas enriched by earlier stars. The Sun formed much later, in a metal-rich region of the disk. When we observe the CMB from Earth, we are looking past the galaxy that made our observing platform possible. The CMB also reaches us through the solar system. The Sun's radiation dominates our local environment, but at microwave wavelengths and after careful accounting, the background remains. Spacecraft observing from L2 avoid some Earth-based complications, but still operate within the solar system's moving frame. Corrections for motion, thermal emission, side lobes, and instrumental behavior matter. The ancient signal has to be measured from a platform that is never perfectly still, never perfectly isolated, and never outside the universe it studies. There is no outside. That may be the most difficult part to imagine. Every map of the whole sky is made from within the sky. Every cosmological parameter is inferred by observers made of late cosmic material, living in one galaxy at one epoch. The CMB gives a view of the universe when it was young, but the view is still our view, shaped by our location and by the paths photons took to reach us. That does not make the view subjective in the casual sense. The measurements are physical. Other observers with sufficiently advanced instruments would measure their own CMB skies and infer similar large-scale laws if the universe is homogeneous and isotropic on large scales. But it reminds us why cosmology relies on principles such as the cosmological principle. The idea that the universe is broadly the same in all directions and locations when averaged over large enough scales. The CMB is one of the strongest pieces of evidence supporting that large-scale uniformity. The CMB is highly isotropic after removing local motion and foregrounds. That isotropy does not mean there are no galaxies or clusters. It means that on the largest scales, the early universe was nearly the same in all directions. The existence of small anisotropies within that isotropy is the crucial balance, too smooth to be chaotic, uneven enough to become structured. The map is a record of that balance. It is difficult to overstate how different this is from the universe of ordinary experience. We live among sharp contrasts, daylight and shadow, hot and cold, mountain and ocean, star and dark sky. The early universe seen in the CMB was uniform to an extraordinary degree. Its differences were tiny. Yet the later cosmos is full of contrast, because gravity amplifies small beginnings. The CMB shows the universe before amplification had done its long work. The oldest light is not bright in our sky, but it is foundational. It is behind the architecture. Behind the spiral arms, behind the galaxy clusters, behind the voids, behind the distribution of matter that telescopes map today. It is the earlier page under the visible writing, faint but still legible if the right wavelengths are used. If one follows the photons backward mathematically, their wavelengths shrink as the universe gets smaller and hotter. The microwave background becomes infrared, then visible, then ultraviolet at earlier epochs in the model, though before recombination the idea of freely traveling photons becomes inappropriate because scattering dominates. This distinction matters. We can calculate the thermal history, but we cannot observe a clean image from before the universe was transparent with photons. Other messengers may someday extend the view. Relic neutrinos would come from about 1 second after the Big Bang, much earlier than the CMB, but they are extremely hard to detect because their energies are tiny and their interactions rare. Primordial gravitational waves could come from even earlier processes. If either became observable in detail, the phrase oldest light would remain true for electromagnetic radiation, but the oldest messenger of the universe might no longer be light. For now, the CMB is the boundary we can map. It is detailed enough to make precision cosmology possible and limited enough to keep the earliest moments open. It is both a success and a frontier. This combination is important. A field with no evidence becomes speculation. A field with evidence and remaining questions becomes science at its most demanding. The old photons continue to arrive. They do not arrive in a single wave that has passed us by. Every moment, more CMB photons cross Earth, detectors, spacecraft, and interplanetary space. The surface of last scattering we see today is not the exact same set of photons measured yesterday, but the statistical background remains. The universe is transparent enough that the ancient radiation keeps reaching us from every direction, one thin shell of past light after another along our world line. As time passes into the far future, the CMB will continue cooling. Its wavelengths will stretch farther, its temperature will drop. Future observers, if any exist in an era of greatly expanded cosmic scale, may find it harder to detect. Distant galaxies may move beyond horizons in an accelerating universe. Cosmology itself may become more difficult in the far future, because some evidence available to us now will be fainter, redder, or inaccessible.
We live at a time when the CMB is cold but measurable, when galaxies beyond the Milky Way are visible, when the expansion history can be traced, when the early universe has not yet faded beyond instrumental reach. This is not a claim of special destiny. It is an observational fact about cosmic timing. The evidence exists now, and instruments have become capable of reading it. A radio dish turns beneath a clear sky. A satellite spins slowly near a gravitational balance point. A telescope in Antarctica scans through dry, cold air. A data archive opens on a screen. The same background is present in each case, waiting behind foregrounds, behind instrument noise, behind the ordinary brightness of the nearby universe. The work is to recognize the ancient signal without forcing it to say more than it says. What it says is enough to reconstruct a vast outline. The universe expanded from a hotter, denser state. It cooled. It became transparent. It contained tiny fluctuations. Those fluctuations grew into large-scale structure. Ordinary matter is only part of the inventory. Dark matter shaped growth. Dark energy affects expansion. The first stars came later. The galaxies came later. The elements that built Earth came later still. Every part of that outline is open to refinement, but the outline itself is written across the microwave sky. The oldest light also gives a practical reference frame. The CMB rest frame is the frame in which the dipole from our motion disappears. The solar system moves relative to that frame, and so does the Milky Way. This does not define absolute space in the old philosophical sense, but it provides a cosmological standard based on the average radiation field. Even motion can be measured against the afterglow of the early universe. The dipole is not usually the part of the CMB that attracts the most attention, but it is tangible. It says we are moving, not just Earth around the Sun or the Sun around the Milky Way, but our local group through the broader cosmic background. That motion is layered with other motions, and separating them helps connect local dynamics to the large-scale distribution of matter. Nothing in the CMB map resembles the constellations people named from the ground. Orion, Scorpius, Cygnus, and the Southern Cross belong to a nearby stellar arrangement, a human pattern projected onto stars in the Milky Way. The CMB pattern is older and more global. It was already encoded before any star in those constellations formed, before the galaxy had its current structure, before the sky could be divided into familiar shapes. Even calling it a pattern can understate the physics. Each feature is the result of initial conditions and processes: gravitational potentials, plasma velocity, radiation temperature, diffusion, geometry, and later propagation effects. The map is a compressed record. Reading it requires unpacking those contributions, testing them against equations, and checking whether the same parameters also explain other observations. There is a patience in that unpacking that matches the signal itself. A rushed interpretation would be easy and often wrong. A cautious interpretation is slower, but it can survive contact with new data. The CMB has survived many new data sets. It has not made cosmology simple, but it has made cosmology accountable. Accountability is why the background remains central even when attention moves to new telescopes and new mysteries. The first galaxies seen by infrared telescopes must fit into the growth allowed by CMB initial conditions. Dark matter candidates must behave in ways consistent with the early universe. Dark energy models must preserve the observed angular scale of acoustic peaks. New ideas can be imaginative, but they must pass through the old light. Some proposed physics changes the number of relativistic species.
Some changes the behavior of dark energy. Some introduces interactions in the dark sector. Some modifies gravity. Some alters early expansion. The CMB constrains all of these because it is sensitive to the expansion rate, perturbation growth, and geometry at early times. A successful alternative must not only explain attention, it must avoid damaging the many things the current model already explains well.
This is why cosmological debates can be both intense and careful. The stakes are high because the questions are basic: how fast the universe expands, what most of its matter is, why expansion accelerates, what happened in the earliest moments. But the evidence is delicate. A responsible answer has to move at the pace of measurement, not at the pace of excitement. The CMB itself has no excitement. It is radiation. It has no memory in the human sense, no intention, no message aimed at observers. Its significance comes from physics and from our ability to understand that physics. That may make it more remarkable, not less. The universe does not need to speak in symbols when its ordinary radiation field contains enough information to describe its youth. In a classroom, the CMB may be introduced as leftover heat from the Big Bang. That phrase is useful. Leftover heat gives the correct broad idea. The universe was hot, and the radiation cooled as space expanded. But in detail, the CMB is also a blackbody spectrum, an anisotropy map, a polarization field, a lensing source plane, a foreground challenge, a calibration problem, and a cosmological ruler. Simple phrases open the door. The real subject begins after them. The phrase "oldest light" also opens a door. It invites a question that is more precise than the phrase itself. Oldest in what sense? Light from when? Why can we see it? Why not earlier? What happened to the photons before then? Why microwaves now? Why is it so uniform? Why are there tiny differences? Each question leads away from vague wonder and into physical cosmology. The answer begins with a hot plasma and ends with a cold map. It passes through expansion, cooling, recombination, last scattering, redshift, discovery, space missions, foreground removal, acoustic peaks, polarization, lensing, and the growth of structure. It is not a short story, because the CMB is not one fact. It is a place where many facts meet. Recombination depended on atomic physics. Last scattering depended on the density of free electrons. The angular scale of fluctuations depended on geometry and the sound horizon. The peak heights depended on matter content. The damping tail depended on photon diffusion. The lensing signal depended on later structure growth. The polarization depended on scattering and quadrupole anisotropies. The oldest light is simple only when seen from far away. Up close, it is a layered physical record. The sound horizon is one of the key scales. It is the maximum distance that acoustic waves could travel in the hot plasma before recombination. This scale becomes imprinted in the CMB, and later in the distribution of galaxies. Because physics in the early universe sets this ruler, and because observations show how large it appears, cosmologists can infer geometry and expansion. A wave that moved through plasma before atoms were stable becomes a ruler for the universe. That ruler is not made of metal or light beams in a laboratory. It is made of a physical process frozen into a pattern. Gravity pulled. Radiation pushed. The plasma oscillated. Then the universe became transparent, and the oscillation phase was recorded in the radiation field. Billions of years later, galaxies still carry a faint statistical preference from the same early waves. This continuity is one of the elegant parts of cosmology. The early sound horizon appears in the CMB as an angular scale, and in galaxy surveys as a spatial scale. Two very different observations, one from ancient radiation and one from the distribution of matter much later, point to the same early physics. Agreement between them supports the model. Disagreement, if it grows, would point towards something important in the expansion history or the measurements. The oldest light is therefore not isolated at the beginning. It reaches forward. It sets scales. It anchors ages. It tests matter content. It constrains expansion. It shapes how later observations are understood. A photon released before the first star can influence how scientists interpret a galaxy survey taken more than 13 billion years later. Of course, the photon does not influence the survey in a causal sense. The data influence the interpretation. This distinction matters because cosmology can sound mystical if stated loosely. The CMB is not guiding the universe. It is informing us about the conditions under which the universe evolved. The power of the background lies in evidence, not symbolism. Evidence also includes what the CMB does not show. It does not show large departures from uniformity. It does not show strong non-Gaussianity in the simplest analyses. It does not show the universe to be strongly curved. It does not show ordinary matter dominating the mass budget. Absences like these are part of the map. They tell scientists which theoretical paths are narrow, which are blocked, and which remain open. A quiet map can be severe. It allows less speculation than the imagination wants. It accepts no idea merely because it is beautiful or strange. It preserves only what the universe actually imprinted and what instruments can actually measure. That severity is why the CMB has become one of the most trusted witnesses in cosmology. Near the end of the analysis, after equations and masks and simulations, the map returns to something simple again. A sky nearly the same temperature in every direction. Small differences across it. A spectrum almost perfectly thermal. A faint polarization pattern. A lensing distortion from intervening matter. From these, the history of the observable universe begins to take shape. It begins not with a calm empty space, but with heat, density, radiation, and particles. It moves through cooling and transparency. It enters darkness without stars. It forms the first light sources. It builds galaxies and clusters. It accelerates in expansion. It produces a solar system late in the sequence. It produces observers later still. The CMB is one of the few pieces of evidence that reaches back to the start of that chain with such clarity. The chain could have been different. Slightly different physical parameters would have changed the timing of recombination, the growth of structure, the abundance of elements, the distribution of galaxies, or the future expansion. The CMB helps measure the values our universe actually has. It does not tell us why those values are what they are in any ultimate sense. It tells us that they can be measured and that their consequences can be followed. There is restraint in that answer, and the restraint is important. The oldest light does not solve existence. It does not close every question. It gives a real surface in the past, a real temperature, a real pattern, a real set of constraints. For a universe as inaccessible as ours, that is already an extraordinary amount to know. If you were to remove the stars from the night sky, then remove the galaxies, then remove the dust and gas of the Milky Way, then remove the dipole from our motion. What remained in microwave light would still not be nothing. It would be the background. Cold, uniform, slightly mottled, older than every visible structure. The darkness would have a temperature. That temperature is not much above absolute zero now, but it once corresponded to a glowing young universe. The cooling from thousands of Kelvin to 7 Kelvin is the history of expansion written into the radiation itself. Every microwave photon is stretched evidence that the universe has grown enormously since it became transparent. The expansion did not stretch atoms in your body, or planets, or galaxies that are gravitationally bound. Local systems are held together by forces stronger than cosmic expansion at those scales. The CMB redshift belongs to light traveling across cosmological distances through expanding space. This distinction prevents a common misunderstanding. The universe expands on large scales. Bound structures remain bound unless other physical processes disrupt them. The photons of the CMB crossed both expanding regions and gravitational structures. Their paths were bent, their energies slightly shifted by some encounters, but they still carry the early thermal pattern. This persistence is one of the reasons they are valuable. The universe changed around them, yet enough of the original record survived to be read. Reading that record has already required generations of instruments. It will require more. Future measurements may improve polarization, lensing, and small-scale foreground separation. New surveys may compare CMB lensing with galaxy lensing over wider areas. Better early galaxy observations may test growth after recombination. Some questions will sharpen. Some may fade as systematics are understood. Some may become deeper because better data make the discrepancy harder to ignore. The oldest light is not finished with us because we are not finished learning how to ask it questions. The photons have already done their journey. The difficulty is on our side: instruments, models, foregrounds, assumptions, and interpretation. The universe has provided the radiation. We are still learning how to read all of it. The deeper the analysis goes, the more the CMB becomes a meeting place between ordinary astronomy and fundamental physics. A galaxy survey may begin with positions and redshifts. A particle experiment may begin with detectors buried underground or arranged around a collider. A CMB experiment begins with a sky that appears almost uniform, yet all three can become part of the same question. What is the universe made of, and how did it change from a hot plasma into the uneven structure we observe now? The background does not answer this alone, but it sets the starting conditions with unusual precision. The Planck Data Archive is not a single picture stored for public display. It contains maps at multiple frequencies, masks, simulations, beam information, likelihood products, component-separated maps, and documentation that allow researchers to test results in detail. A cosmologist working with those files is not simply admiring the early universe. They are checking how a detector responded, how a foreground model was built, how uncertainties propagate, and how much a conclusion changes when assumptions are adjusted. This is one reason the CMB remains useful years after a mission ends. The spacecraft stops observing, but the data continue to be interrogated. There is something almost archaeological about that work. Though the tools are mathematical rather than brushes and field notebooks, the ancient layer is not buried under soil, it is buried under foreground emission, detector noise, calibration effects, and the later universe itself. Researchers remove one layer, then another, then test whether the remaining pattern behaves like a cosmological signal. If it does, they compare it to models. If it does not, they ask whether the model is wrong, the subtraction is incomplete, or the instrument has left a mark of its own. This is also why the same CMB map can be used by scientists with different goals. One group may focus on the 6 basic parameters of lambda CDM. Another may test whether the number of neutrino species differs from expectations. Another may reconstruct lensing. Another may search for signatures of cosmic strings, early dark energy, isocurvature modes, or departures from statistical isotropy. Most proposed signals are constrained rather than detected. That may sound less dramatic than a discovery, but constraints are how the field keeps its speculative ideas attached to measurement. A theory about the beginning of the universe can be beautiful and still fail the microwave sky. It can solve one problem and create three others. It can ease attention and damage the acoustic peaks. It can fit temperature and fail polarization. The CMB is difficult to evade because it is so information-rich. It does not test one number. It tests a pattern across scales, frequencies, and correlations. To change cosmology successfully, a new idea must pass through that whole pattern without leaving contradictions larger than the problem it was meant to solve. This is why even a small improvement in measurement can matter. A better optical depth to reionization changes the inferred amplitude of primordial fluctuations. A better lensing reconstruction tests the growth of structure. A cleaner polarization map narrows the space for primordial gravitational waves. A better foreground model can turn a possible anomaly into a known contaminant, or make a persistent feature harder to dismiss. Precision does not remove mystery, it makes the mystery more specific. The CMB is also used to estimate the baryon density, the amount of ordinary matter in the universe. This estimate agrees remarkably well with the abundance of light elements expected from Big Bang nucleosynthesis. That agreement links physics from the first minutes to physics hundreds of thousands of years later. Deuterium observed in distant gas clouds, helium abundances, nuclear reaction rates, and microwave acoustic peaks are not the same kind of evidence. Their agreement is therefore important. It suggests that the broad thermal history is not being forced onto one dataset, but appears in different relics of the early universe. When evidence separated by time, method, and physical process points in the same direction, the conclusion becomes harder to avoid. The CMB is not alone in supporting the hot Big Bang model. It is joined by cosmic expansion, light element abundances, and the growth of structure. But it is the CMB that gives the model its most direct ancient light. It is the background that turns the early universe from an inferred hot state into something that left a measurable glow across the whole sky. The glow is so uniform that its existence once seemed almost too smooth for a universe filled with galaxies. Then the anisotropies were found, and the smoothness became part of a more precise balance. The universe was not chaotic at recombination. It was not featureless either. It contained differences small enough to preserve large-scale order and large enough to let gravity build complexity. This is one of the most important facts the CMB preserves. Not violence, not emptiness. A nearly smooth beginning with just enough structure to matter. There are still alternative cosmological ideas, and some are useful even when they do not replace the standard model. They ask whether dark energy changes with time, whether dark matter interacts with other particles, whether gravity behaves differently on cosmic scales, whether early energy components affected the sound horizon, or whether inflation had a more complicated history. The CMB does not forbid asking these questions. It disciplines them. Any answer must keep the observed microwave sky intact. The sound horizon has become especially important in discussions of the Hubble tension. If the early universe ruler inferred from the CMB is changed, the inferred expansion rate can shift. Some models introduce new physics before recombination to alter that ruler. But changing the early universe is not easy, because the CMB power spectrum is tightly measured. A modification that helps one number may disturb peak heights, damping, polarization, or structure growth. The oldest light is flexible enough to inspire new ideas, but strict enough to reject many of them. Late universe measurements have their own complications. Cepheid variables must be calibrated. Supernova samples must be standardized. Dust must be corrected. Gravitational lensing surveys must understand galaxy shapes, redshifts, and intrinsic alignments. Cluster counts depend on mass calibration. No side of a cosmological tension is free from systematics. The CMB is precise, but model-dependent. Local measurements are direct in a different way, but dependent on distance ladders and astrophysical calibration. The tension matters because both sides have become sophisticated. If the tension eventually disappears, the CMB will still have served its purpose by forcing better measurements. If it remains, the background may help reveal where the new physics must enter. Earlier than recombination. During recombination. In the growth of structure. In dark energy. In gravity. Each possibility leaves different marks. The oldest light is not only evidence for what happened, it is also a filter for explanations of what may be missing. The same is true for the cold spot and other large-scale anomalies. They continue to be examined because they are visible enough to ask about, but not decisive enough to settle the issue. Some explanations invoke a large underdense region along the line of sight. Some invoke statistical chance. More exotic ideas have been proposed, but extraordinary explanations require more than visual strangeness. The CMB allows mystery, but it does not reward overstatement. A responsible account of the CMB, therefore, has to hold two facts together. The map is one of the strongest confirmations of the hot Big Bang framework. The map also contains features, tensions, and limits that keep cosmology from being complete. To emphasize only the confirmation would make the story too tidy. To emphasize only the anomalies would make it misleading. The real situation is more interesting, a remarkably successful model under active pressure from increasingly precise evidence. Future instruments may not produce a single iconic map that replaces Planck in public memory. They may instead produce improvements in particular measurements, lower noise polarization maps, better lensing maps, improved foreground separation, stronger cluster catalogs, and sharper constraints on inflationary gravitational waves. The progress may look technical from the outside, but technical progress is exactly what a mature field needs. The biggest questions now hide in small differences. There is also a practical limit to how perfect CM temperature measurements can become, because Planck already measured much of the primary temperature anisotropy close to the cosmic variance limit over many scales. Polarization and lensing still offer more room for improvement. Small-scale observations add secondary science. Cross-correlations with galaxy surveys become increasingly powerful. The next era is less about discovering that the CMB exists and more about using it as a precise tool across cosmology. That tool began as radiation in a universe without planets. It became a prediction in equations, an unexplained hiss in a horn antenna, a blackbody curve from a satellite, a modeled map from COBE, a sharper all-sky pattern from DoubleMap, and a high-resolution relic from Planck. Now it is a dataset used to weigh the cosmos, measure geometry, test inflation, trace dark matter, and challenge the expansion rate. The same light keeps changing roles because our questions keep becoming more exact. One can imagine a researcher late at night comparing a model curve to a CMB power spectrum. The plot is not visually dramatic. It is a line through points with error bars. But in those points are oscillations from a plasma that filled the universe before atoms were stable. In the curve is an attempt to describe matter, radiation, geometry, and time, with a small set of parameters. The distance between the line and the points is where confidence or trouble begins. That is how the oldest light often appears in real science. Not as a glowing horizon, not as a voice from the beginning, as residuals, as likelihoods, as calibration files, as small deviations from a model, as a foreground that has to be understood before it can be removed, as a signal that becomes meaningful only after patience has turned faint radiation into evidence. The result is a universe that is knowable in pieces, not fully transparent to thought, not completely hidden either. The CMB gives one of those pieces, perhaps the most ancient piece available to electromagnetic astronomy. It is a boundary, but it is also a foundation. It tells us where the visible story can begin, and it reminds us that before the first star there was already structure waiting in almost imperceptible form. The precision also changes the way older discoveries are remembered. Penzias and Wilson did not need a full sky anisotropy map to prove the background existed. Kobe did not need Planck's angular resolution to show that fluctuations were real. Each stage answered the question its instruments could address. Later stages did not make the earlier ones obsolete. They extended them. The discovery of the glow, the measurement of its spectrum, the detection of its anisotropy, the mapping of its peaks, and the study of its polarization are separate steps in one long measurement. This matters because science rarely arrives as a finished image. It arrives in layers of adequacy. First, a signal becomes distinguishable from noise. Then, its basic properties are measured. Then, its small variations are detected. Then, those variations become precise enough to test models. Then, the remaining disagreements become important. The CMB followed that path. What began as excess microwave noise became a tool for estimating the age, contents, geometry, and growth history of the observable universe. Even now, the map continues to be reinterpreted as other fields improve. Better measurements of galaxy clustering change comparisons with structure growth. Better supernova calibrations sharpen expansion debates. Better dust maps improve foreground separation. Better simulations of galaxy clusters refine secondary anisotropy studies. The CMB is fixed in the sky, but its scientific meaning develops as the rest of astronomy becomes more precise. There is a danger in treating the CMB as if it belongs only to the past. Its photons were released in the past, but the measurement happens now. The interpretation depends on current instruments, current models, current foreground knowledge, and current statistical tools. A future experiment may not change the ancient photons, but it may change what we can reliably extract from them. The evidence is old. The reading of the evidence is not. This makes the oldest light feel less like a closed chapter and more like a permanent reference. Whenever a new claim is made about the early universe, the CMB waits as a test. Whenever a new measurement changes the expansion rate, the CMB becomes part of the comparison. Whenever a theory proposes new particles or fields, the CMB asks what those additions would have done to the plasma, to the peaks, to lensing, or to polarization. A universe that can be tested in this way is not fully beyond us, even when it exceeds intuition. It is too large to hold, too old to visit, and too complex to summarize completely, but not too remote to leave evidence. The cosmic microwave background is one of the clearest examples of that. It does not bring the beginning into reach, it brings one early surface into measurement. And that is enough to change the scale of everything around it. A star becomes a later object, a galaxy becomes a later structure, a planet becomes a very late condensation of heavy elements. Human history becomes a trace near the end of a long expansion. Behind all of it, the microwave background remains, not brighter than the rest, not more dramatic, but older, colder, and more fundamental than the visible sky first suggests. In the end, the cosmic microwave background is not only about the early universe, it is about the relationship between observation and origin. We cannot stand at recombination. We cannot watch the plasma clear. We cannot see the first 380,000 years with ordinary light. But the radiation released then still crosses our detectors. A boundary in time becomes a map across the sky. The map is faint. The colors are artificial. The differences are tiny. The analysis is difficult. The foregrounds are real. The uncertainties remain. And still, through all of that, the conclusion survives. The universe was once hot enough to glow everywhere, dense enough to trap its own light, and then cool enough to let that light go. That released light has been traveling ever since. It passed through the formation of the first stars without stopping. It crossed the growth of galaxies and clusters. It moved through a universe becoming richer in elements, dust, planets, and magnetic fields. It entered the era of telescopes, radio antennas, satellites, and cryogenic detectors. It arrived as a microwave whisper from a time before there were worlds. When a CMB map appears on a monitor, it is easy to see only the oval, the mottled colors, the familiar caption about the oldest light. But behind that image is a physical event, the universe becoming transparent. Behind it is a measurement, a black-body glow at about 2.7 Kelvin. Behind it is a pattern, fluctuations at 1 part in 100,000. Behind it is a history, the growth of everything visible from almost nothing visible at all. The map is quiet because the signal is quiet. Its meaning is not. Somewhere, a detector continues to measure the microwave sky. It does not see the stars first. It sees through them, around them, and beyond their era toward the old radiation that fills every direction. The data arrive as numbers, not revelations. The numbers become maps, the maps become tests, the tests become a history written with uncertainty and care. And behind the foregrounds, behind the noise, behind the young light of galaxies, the oldest light in the universe is still there, almost uniform, slightly uneven, still crossing space, still carrying the first clear image the cosmos ever allowed itself to send.